Here we see a plot of the distribution of heads on 6 flips of a coin. We have few occurrences of no heads, few occurrences of 6 heads, relatively more occurrences of 3 heads, tailing off as we move out toward the extremes of 0 and 6 heads. And you're familiar with this from the work you've done with permutations and combinations. The probability of a 3 is what? Well, it's the number of ways of choosing 3 out of 6. In other words, 3 of the 6 coins have to come up heads out of the 2 to the 6th possible outcomes that you can have. Now you could list the 2 to the 6th or 64 outcomes: heads, 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 tails, and so forth, all 64 of them, and you'll see that 20 of them do come out with 3 heads. But you also should know that the number of ways that can happen is given by this combination. And also that when you flip 6 coins, there are 2 possible outcomes for each, and the fundamental counting principle tells us that there are therefore 2 to the 6th or 64 possible outcomes. Now again, I'm not going to go through the details of evaluating these. That's a topic for the previous chapter on counting and on permutations and combinations. In any case, we see that the probability of getting 3 heads is 0.31. The probability of getting 4 heads, well, we're choosing 4 out of 6. So it's a combination of 6, 4 out of 2 to the 6th. That combination 6, 4 is 15. That's out of 64 possible outcomes, so we have 0.24. Then to get 5 heads, there are combination 6, 5 or 6 ways out of the 64 for probability, approximately 0.09. I'm just rounding these off to the nearest hundredth, so they're not necessarily going to add up to 100%. There's only one way to get 6 out of 6. Combination 6, 6 is 1, and that gives us a probability of roughly 0.01. Actually, that comes out closer to 0.02. Comes out 0.01 something, 0153, 0154, something like that. Okay. Now, of course, the probability of a 2, the probability of a 1, the probability of a 0 are identical to the probabilities of a 4, a 5, and a 6. So these probabilities would be 0.24, 0.09, and 0.02. And if we were to add all those probabilities, let's see, we'd get 0.11, 0.35, it'd be 0.70. It actually comes to 1.01, 101% with my round off. But if you put the exact figures down, it'll come out to 100%. And the numerators here will add up to 64 if you include all 7 of these bars on the bar graph. The point now is that if you take this is the binomial distribution, of course, and again you should be familiar with that name and that idea by this point. If I draw a curve approximating this distribution, we get this bell-shaped curve. And if we take more and more heads, or more and more coins, the curve gets closer and closer to a perfect bell-shaped curve. And here's a picture of not a perfect bell-shaped curve, but the best hand sketch I could come up with, to what's called the normal distribution. This is the bell-shaped curve, and you can think of this as the curve you would get if you had a whole lot of coins. And your book talks a little bit about this also. I'll write down the formula for this curve if you like. Whether you like or not, I'm going to write it down. You can skip over it if you like. You don't really need to know it. But the probability distribution function we call P of z. It's a function P of the variable z, where z is the number of standard deviations from the mean, the z-score that we calculated and looked at in the last example. And this is going to be 1 over the square root of 2 pi times e to the negative z squared over 2. That's a formula for the curve. You can put that into your calculator and get the height of this curve at any point. Now it turns out that if you put the numbers into the curve, for z equals 1, put that into here, and z equals 0. Of course, if you got z equals 0, the probability will be 1 over the square root of 2 pi. For z equals 1, it'll be that times e to the negative 1/2. It turns out that then at z equals 1 and negative 1, if you analyze this function, again, you don't have to know how to do that. I'm just telling you where it comes from. But you certainly could do that if you wanted to. In any case, the height of the curve at z equals negative 1 and z equals 1 is about 60% of the height in the middle. And at z equals 2 and negative 2, it's about 13 or 14% of the midpoint height. I've got 0.14 down here. That'll do for an approximation. You could actually figure it out on your calculator if you wanted to. But there's really no need to, unless you're very curious about it. These numbers come from this formula. This formula comes from a limiting process on the binomial distribution, which requires a whole lot of calculus and a whole lot more knowledge than we're talking about in this course. Using calculus and approximation methods, in fact, we find that the area under this curve from z equals 0 to z equals 1 is about 34% of the total area. And between z equals negative 1 and z equals 0, there's another 34%. This curve is perfectly symmetric around z equals 0. Between z equals 1 and z equals 2, we've got about 14%. And beyond z equals 2, we've got about 2% of the total area under the curve. And those numbers should make sense. If you think of cutting this out of a piece of cardboard, then if you cut this out, what you get here would weigh about 34%, a little more than 1/3 as much as the whole cutout. And what you get here would be a little more than another third. What you get here would be about 14%. What you get here would be about 2%, and so forth. And that's the general characteristics of what we call the normal distribution. And we want to keep in mind that that's just a limiting function for the binomial probability distribution here.